All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. When I was coming to work this morning, I was biking on a bike path, and I went around a corner, and there was a gaggle of goslings on the ground. And geese can be really mean at the best of times. And when there are goslings involved, they somehow get meaner. And so there was like these adult geese that were like hissing at me as I was going by on my bike. But I don't know, damn, goslings are cute. They are so adorable. That yellow fluffy feathers is just like, is the tops. But yeah, geese are so mean when they've got goslings. Geese are so mean when they've got goslings. I hope that you're doing all okay. I saw a bunch of you at the CS Symposium last night. I saw lots of other people at the CS Symposium last night. If you missed out, it's the third time that it's been done, so I believe it will be annually at this point. I think it's safe to say that it's annual. Rob was really nervous about calling it the first annual CS Symposium, but 3 times in, I think it's safe to call it the annual CS Symposium. By the end of today's lecture, what I want you to be able to do is I want you to be able to show how common file operations are performed in terms of manipulating a file system's data structures. So everything that we've done so far in the class has been kind of limited to like, how do you open a file and how do you read a file? And today what I want to do is spend a little bit of time thinking about how the data structures in these 2 file systems that we've been thinking about would change if we were to append to an existing file. So this is one of the ways that we're going to manipulate our file system's data structures and then be able to think about what data structures are changing as a result of these operations. The other thing that I want to do is I want to spend a little bit of time thinking about inconsistent file systems. So these 2 things kind of go hand in hand. We're going to be spending time thinking about how we're going to manipulate a file system's data structures. And one of the key things about manipulating or changing a file system's data structures is that while this idea of writing to our hard drive a single sector, that is an atomic operation. So we're going to write 512 bytes. We're going to update some data structure that's within 512 bytes. That will either complete or it will not complete. But when we think about the high-level volume overview, the high-level volume structure of these things, the data structures that we're manipulating are really far away from each other physically. They're not going to be in the same sector. So the fat and the cluster heap are very far apart from each other, especially as you get further and further into the cluster heap. So it's not really possible for us to do these updates atomically. It's not going to be possible for us to do these updates atomically. That kind of means that we might be in the middle of a logical update operation. I'm making this file bigger, and our system crashes. And now we've got some of the data structures updated and some of the other data structures not updated, and they don't agree with each other anymore. One data structure says this, our allocation structure says this many blocks are used, but if we go through the inodes or the directory entries, not that many blocks or clusters are actually used. So I want to be able to think about these kinds of inconsistencies. And I want to be able to think about what's it going to look like if me or mom or dad open up my Windows Explorer or Mac OS Finder or my Linux file browser, and I look at it, what are they going to see? What are they actually going to see as a result of these inconsistencies in the file system's data structures that we've got? First and foremost, I promised that I would have another Q&A session about assignment 1. I'm going to hard limit this to 10 minutes today. I'm going to set my timer for 10 minutes. So if you want to ask a question, please join the Mentimeter that I'm going to start right now. And if I am not able to get to your question in today's class, I'm going to politely ask you to ask that question on the course forum so that I can actually answer the question that you might have about that. So I'm going to hold this up here for about 30 more seconds, and then I'm going to switch to Mentimeter, and I'm going to start a 10-minute timer on my clock. Just confirming before I switch to Mentimeter, you've been able to join, okay? Yeah, okay, awesome. All right, I'm gonna switch over to the Mentimeter and I'm gonna hit play on my timer here. So the question is the allocation map used for A1? You mean the allocation bitmap? Yes, whoever asked that, I think so, I think so. For A1, no, it's not gonna be used for that. It's a structure that I want you to be aware of in terms of EXFAT has an allocation structure in the same way that EXT2 and VSFS have, but it's not gonna be used for anything in assignment 1. How to check if the file system is mounted on NQP Open? That's a fair question. So when I implemented this, the approach that I took for doing the mount operation was to have a file scope variable. Someone reminded me previously that you might not have thought about the words file scope variable for quite a long time. This is the similar idea to a static class variable in Java. So this is a variable that resides outside of any functions that you've got. When I implemented this, what I did was I had file scoped, so outside of all my functions, an integer that represented the file descriptor, and I set that by default to -1, and then only upon a successful mount did I change that to some positive integer, so that when I did call NQP open or NQP read, I could just very quickly check and see, is this not equal to -1 at the file scope? And then I know that this thing is mounted. If our code runs with some of the volumes, but not all, as in it results in seg fault or something like that, will we still only have at most 50% of our grade? That's a fair question too. When I'm asking the graders to do assessments on the outcomes, they're going to use certain volumes for certain things, and you're going to be able to achieve certain levels based upon those volumes. In some cases, they're only using like the one file volume to do things. So like to have, for assessing the idea of having read from file A and then read from file B and then read from file A and read from file B, this interleaving structure. When I ask the graders to assess this, what I'm asking them to do is run the paste program and run it with the one file volume and run it with readme twice. So it's just like opening the contents of the readme and it's just sticking it right beside each other there. So in that sense, there are not necessarily all the volumes are going to be used for assessment. I however, can't guarantee that they're not going to use the one that's causing your seg fault. I'm not sure if you're asking this question because you're getting a seg fault right now on some of the volumes versus not. But if you are getting a seg fault on some of the volumes, I think I might ask for a question to be asked on the forum with a little bit more detail about what's going on, or either coming to see me or coming to see me during my office hours. Tips for programming the open function. I'm not sure how much you're looking for here, but I can give you my high-level overview of what I did for this. When I was working with the open function, the approach that I generally had was that I'm being passed a string that has forward slashes in it to separate different parts of the path that I've got, and I'm tokenizing that string. So I use the function stir-sep for that, strsep, but strtoke is the same thing. It's accomplishing the same task in the end. So I'm going through this and I'm starting from the root directory and I'm looking for things that are named the first token. And then after that, I'm going to start looking for the next one, for the next token, if I'm able to find the first token in the root directory. I change to that directory in my logic. My approach to this was to build the complete set of entry sets for a directory before I even start searching for stuff. This is really inefficient. This is really crazy inefficient because I was doing things like building the entire entry set for a directory for all files in the directory, even if it's the first thing that I'm looking for. But for me, logically, that meant that I was able to separate these concepts of like build up entry sets and then find something in the directory. it's super inefficient. It is super, super inefficient. And you might have noticed that when I did that ls on that one volume and it was just taking so long to print everything out. It's because every time I was trying to look for one of those files, it was building up an entire entry set for that directory. It is crazy inefficient, but that was my idea. And the reason I did that is just for me, it's easier to separate these things up into parts. I'm not sure that I can be much, much more specific than that, but I hope that that's helpful. Some functions are not on the rubrics. How are they assessed? So like close, I think, is not in the rubric. I think that's one of them. Is there another one that I'm not thinking about? The volume label is also not in the rubric. You're right, it's not in the rubric. They are going to be assessed in that the vol label function is being called by the ls program, and it'll be called by the ls program. So you'll either get something there or not. The close function is not going to be assessed. It's just not going to be assessed. It's not part of the assessment that we're looking for. When you say we should be able to open multiple files, does that mean multiple files in the same volume or multiple volumes? This is to mean the first one. So multiple files in the same volume. And it might even be the same file in the volume multiple times. So as I was saying, when we're thinking about doing the file A and then file B and then file A and then file B, I'm going to ask the graders to run paste with readme.md and readme.md. So it'll be the same file that's being opened twice. But there should be different kind of metadata kept about each of those things. What happens when you mount and mount again? Does it reset all files or fail? Also, when you unmount, does it return success if you never mounted in the first place? I'm gonna answer like a meta question here, and the meta question is I'm not gonna do stuff like this. I'm not gonna give you weird edge case scenarios like this where we're gonna have code that's like trying to force your code to fail. That's not my goal with this assignment. I don't want to try and force your code to fail, so I'm not gonna ask further graders to run any code that calls mount and then mount again without having previously unmounted the old volume. However, I guess what I'd say about this in the context of the question itself is that if you called mount after calling mount, then the second mount should just fail because there's already something mounted. If you unmount without mounting something, does it successfully not unmount something? I guess yes, I guess yeah. But I'd say that the precondition for unmount ought to be that something has previously been mounted. So it should probably fail in that case. Do we need precondition checks and postcondition checks for all the functions we write? Minimally, I'd say that you should have it for the functions that you're being assessed on. Maximally, I'd say it should be everywhere. When I do this stuff, it's sanity checking for me. An example of this is when I did this function that builds up all the entry sets for a directory. The entry sets are in a specific order. They have to be in the order of file, stream extension, file name. And I have assertions, these are partly invariants in my code that say I shouldn't be looking at a stream extension right now if I have not previously seen a file. That's not a state I should ever be in. And so I make sure to encode that stuff mainly for myself. I don't want to get into that state where I'm kind of messed up in the middle. I also want to stop myself from like sending null to my functions unintentionally. I want to stop myself from sending invalid values to my functions unintentionally. So the functions that you write in support of what I'm asking you to do don't require it necessarily, but I'd encourage you to at least think about these ideas to include that in your implementation. But the ones that I'm assessing you on, those are the ones that the graders are for sure going to be looking at for that. If our code is messy, is that okay? One thing I guess I'd say about this is you should try to use a code formatter. Visual Studio Code, I believe, has code formatters built into it. Yeah, somebody's nodding. So yes, it has code formatters built into it. There's also a command line tool called Clang Format that can help you with this. In terms of messy, like indentation is all messed up or like curly braces are all messed up, that it'll help with that. If your code is messy, like you're declaring variables all over the place, I'm going to leave it to the discretion of the graders to make a judgment about how messy or unreadable your code is in terms of their assessment. But I'm very happy for you to ask me questions later. Like if you think that they were overly harsh about their assessment of the messiness of your code, please just come and talk to me and we can take a look at it together. Do we explicitly need to build a linked list for the fat chain? No, you don't explicitly need to build a linked list for the fat chain. In fact, I did not build a linked list at all for this assignment. I only look up the next cluster when I need to look up the next cluster. So I will go to the fat only when I need to actually find out what the next cluster in the cluster chain is. All right, so that was my 10 minutes. As I said, if I wasn't able to answer your question here, please ask it on the course forum, and I will answer it either after class or before class tomorrow. And then we're going to keep on moving with some other stuff here. So I'm going to pop back to my slides. And what I want to start working on right now is I want to finish up the example that we were looking at last class. So last class, we spent a lot of time taking a look at an EX2 formatted volume using this hexdump tool. Hexdump is a bit of a painful tool to use for something like this, but I want to emphasize that my goal here was we've got documentation, and using that documentation, we're able to actually navigate through the file system's data structures, even in this hexadecimal format, even in this binary format. We're ultimately able to get to the contents of a file using a tool that is pretty primitive. There's a bunch of like kindergarten kids walking by out there.
I think they might be from the stadium. There's like a sports event happening.
There's sports events at the stadium, okay. Because now it looks like they're going like this in a circle. And Mini U doesn't start for a while, so.
You're not a walk over, they're all like cheering.
Okay, okay.
Very
Children chanting in the background, yes.
Yeah.
Sounds like a bit of a horror movie, yeah.
Yeah.
So anyway, I'm digressing here. We spent a lot of time taking a look at this in hexdump. There's a suggestion of File Explorer. If you wouldn't mind posting a link to that in the forum, I think that would be cool to have a reference to that. Just for everybody to see. I don't know, is it a web tool? Is it something you install? File Explorer, you said it was called File Explorer? Windows File Explorer, I thought you were talking about some really cool like hex utility that would highlight all this stuff. You were just talking about actually opening up Windows Explorer. Okay, we'll post a link to that on the course forum and everybody will know about it. Okay, so my goal with this again was we can take this documentation and we can actually find our way through this file system. And it's inscrutable. This is hex, like, and I guess I want to be clear. I want to make sure that I'm clear. 256 kilobytes of hexdump output would take about 75 pages of text, and that's not going to appear on your test. It will not appear on your test in any way, shape, or form. I don't want to kill a forest asking you questions about this. We can navigate our way through this file system, given information about the data structures that are in it, but it's painful. And so what I want to do now is finish up what we were working on last class by starting to find our way at least to the directory entries for the root directory in a C program using functions like lseek and read. I put up where we left off in this Git repository. So if you were following along last class, if you want to get to where I am right now, you should pull this. If you were following along with where we were at, then you might also be just in the right spot right now. But I'm going to pop over to my terminal, and I'm going to open up the ext2 inspect.c program that we were looking at before. I'm going to make this a little bit bigger, and then I'm going to ask at the back, is that big enough for you? Okay, awesome. I'm getting some thumbs up. I'm going to go right down to the bottom, and one thing about this summer course, while it is really fast, this was just yesterday, so I don't really need to spend a lot of time reminding you of what we were doing with this code in class yesterday. So the place where we were at was that we had just finished reading in our super block, and we're in the state of we want to get to where the block group descriptor table is. So we read in the super block, we confirmed that the magic number is what it is supposed to be, and we've calculated what the block size is using this expression 1024 left shift superblock.log block size. For the record, I didn't just know this. This is in that web page. This is in that documentation that describes this specific expression in the one that I linked to in the class last time. So once we know that, then we're going to be able to go to the block group descriptor table. And this is the first block after the super block. So this is effectively the same as going to block 1 in this file system. So I'm going to lseek using the file descriptor that we've got, and I'm going to go to that expression, 1024 superblock.log block size. And I want to go seek set. I want to go to this location as an absolute offset. I want to go directly to the first block in this file system, which is where my block group descriptor table is going to be. Once I'm at the block group descriptor table, then I can start reading in the first block group descriptor. There is only one in this tiny file system that we made, but this is a table. There might be many block group descriptors, but there's only one because we made such a tiny, tiny file system when we made this in the first place. So to read this, I'm going to do something similar to what I was doing with the super block. I'm going to read from the file descriptor. I'm going to pass to it. I'm going to scroll up because I can't remember the name of this variable, and I'm going to come back down. It's called group DESC. And what I want to read into that is the size of this structure. And the structure itself is called, I got to go back up, sorry, ext2 underscore group desk. So that's going to read in our block group descriptor table. And now we're going to be able to ask questions about what we had in that block group descriptor table. And this is where we were able to start finding other structures in the file system. So remember that our super block in this file system doesn't really tell us where other stuff is in the file system. With ext2, we have to go to this block group descriptor table, and that's where we're going to find things like the inode table and the other references to the data that we've got here. So the information that I'm going to get from this is stuff like the block allocation structure. The block bitmap is at block D. And this is group underscore desk dot block bitmap. I can say that the inode bitmap is at block something else. And the very last thing, and the most important thing for us right now, is where the inode table itself is. So the number that we're getting in this group descriptor refers to the block number that contains our inode table structure. So now that we know that, I want to go to that location. We want to go to the inode table itself. Our goal here is to start finding the root directory's inode so we can start going to the block that contains the directory entries for the root directory here. So to get to the inode table, I'm going to use lseek again. On the file descriptor that we're working with, I'm going to do 1024 left shift superblock.log block size. And I want to multiply this by group descriptor table dot inode table. So our expression here is, this is how big one block is, this left shift expression, and I want to multiply that by the actual block number for the inode table itself. That's the number of bytes that I need to seek into this volume to get to the inode table. I want to do this as an absolute offset. Our block structure here starts at block 0. Super block here is block 0. And I want to go to the nth block exactly from this location. So I'm going to do it as an absolute offset. Once I'm at the inode table, we want to find the inode for the root directory. Root directory is inode 2. This is a fixed value in this file system. We don't have to ask the superblock what the first inode is for the root directory. With ext2, it is just fixed at inode number 2 represents the root directory of this file system. So I want to go to inode number 2, and my location right now is I'm at the start of the inode table. I'm at inode number 1. Inode number 1. Remember that this is a 1-based array and not a 0-based array. I'm at inode number 1. And I want to find the inode that contains the root directory. So I'm going to use lseek one more time here, file descriptor. And this time what I'm going to say is 2, I'm hard coding this. This is the root directory. -1, this is off by 1 arithmetic because the first inode, the first entry in the inode table is inode number 1. And I want to multiply this by 128. I'm hard coding this again because recall that when we started making this file system, we set the inode size to be 128 bytes. So every inode in this table is going to be exactly 128 bytes. And the difference this time is that I don't want to do this as an absolute offset. I want to do this as a relative offset. So from where I am right now, I'm at the beginning of the inode table. I'd like to seek this many bytes after where I am right now, as opposed to calculating an absolute offset. You could do this as one lseek with an absolute offset here. You could do this expression plus this if you want. But for me, I like to do it this way. I want to get to the start of something, and then I want to get to the thing that's inside the thing that I've gotten to in the first place. So I just separate these two things out as two separate steps here. So once I'm at inode number 2, I should be able to read the root directory's inode. And so I'm going to read into, from the file, the name of my variable is, I'm going to come back here in a second, root inode. And I want to read size of, and the structure here I believe is, well, it's nothing, because I'm going to hard code this as 128. Our inodes are 128 bytes in size, so I'm just going to ask to read 128 bytes into that thing. I'm going to print out the root directory's first block pointer is. I'm going to print this out as a decimal number. And the root directory's first block pointer is going to be the first entry that I have in that block pointers array. I'm going to pop open another terminal here on the bottom. I'm going to make this, and I'm going to run it with the volume. And if you can recall all the way back to yesterday when we were doing this, like stepping through our file system with hexdump, the first block for our root directory was in fact 5. It was the 5th block that we were looking for, and we had to go to location 5000 in hex to be able to get the directory entries for this root directory. So our root directory's first block pointer is 5, and we confirmed that visually last class by being able to do that. So now that we're able to find the root directory's first direct block pointer, now we can start going to that block and reading directory entries. The data that's in that directory in that block is going to be the set of directory entries that represent all the files that are in our root directory. And so we're going to be able to go to that location and start finding what we want. So to do that, I'm going to use lseek. I'm going to go to, from the file descriptor that I've got, 1024 left shift superblock.log block size. And I'm going to multiply that by root inode.block pointers at 0. And for this, I want this to be an absolute offset. I'm going to a specific block, so I'm going to use an absolute offset here to get to that location. So at this point, now we should be at the beginning of the root directory's directory entries. The first thing that I'm expecting to read from this is the directory entry that represents that dot. So that self-reference back to this location. The next one is going to be ... and that's also a self-reference back to this one because the root directory is a special case that has a parent of itself. And then after that, I ought to be able to find a couple of things. I ought to be able to find the directory that is called lost plus found, and then I ought to be able to find readme.md. These are just file names right now, and they are going to contain an inode reference to where the data for that thing actually is, but we're going to stop at looking at the directory entries here and printing them out. Following the directory entry to its block then would be the next part of this exercise, but we're going to stop taking when we get to the point of reading these directory entries out. So I'm at the beginning of the root directory's directory entries, and so I'm going to start reading from this file into a variable that I've got. I'm going to go up one more time here. That's called, I think it's called dir entry. It is called dir entry. And then the other thing I'm going to be using here is called file name, which is a character pointer. I'm going to read from this, and I'm going to say dir entry, and I want to read size of, and the type, I believe, is ext2 underscore dir entry. So this is going to read in the very first directory entry in the root directory. I'm going to say, for now, printf, the entry's inode is %d, dir entry dot inode. I want to print out the entry's record length. The record length here is something that indicates effectively where the next thing is, where the next entry is that we're going to be able to load once we get to that point. The name length is the file name's length that we're looking at. And then finally, we've got the type. And so this is what represents whether or not it's a file or a folder. I'm going to write this. I'm going to make it. I'm going to run it. And the very first thing that we're seeing here is a record that has a name length of 1. This is that dot. This is that dot entry that we saw when we were looking in our output from hexdump. I want to be able to print out what the file name is. And so I'm going to have to do this dynamically because the records here have a dynamic length. It can have 0, unclear why we can have 0 characters, but it can be 0 up to 255 total characters in the file name in this record. So I'm going to say here file name is equal to malloc size of char. I'm going to allocate a string. I'm going to multiply this by dir entry.namelength. And I'm going to add 1 to this. I want to be able to allocate this with a null byte at the end of it. The strings that we're getting out of these directory entries do not have null bytes in them. So I have to explicitly allocate this null byte at the end. I'm going to do a little trick here for myself, which is I'm going to start by initializing everything in this variable to 0, or the null byte. I could go back later and say the last element in the array is equal to the null byte, but I'm just going to blindly set everything to be the null byte so that when I do read something into this, I can assume that it is null byte terminated. So I'm going to set the contents of file name to be 0, and I'm going to do that for dir entry.namelength +1. Then I'm going to read the name. We just finished reading this directory entry type, and so our offset right now is at the first character of the file name. So I can start reading the file name immediately from the file that I'm in. So file descriptor, file name, and I want to read into this dir entry.namelength. So I don't want to do the +1 here because I don't want to read past the end of it. I just want to read all the characters that are specified to be in the file name itself. I'm going to print out the file name. And then I'm going to free the file name. I'm not using it anymore after that. I'm going to make this. Man memset. I need string.h. I'm going to go to the top of my program here for a second, and I'm going to include string.h. I'm going to go back to the bottom where we just were. I'm going to make this again. I'm going to write my file. I'm going to make it again. There we go. And the file name is dot. Okay, so exciting. Yes, we've got to the first directory entry for the root directory, and we've got this dot printed out. But there's more than one file in this directory, and I want to read all the files in the directory. And so I'm going to have a loop here. The loop structure here is going to be a little bit different than what we're expecting to be. I'm going to start by reading the first directory entry, and then what I'm going to put in here for now is while 1. I'm going to indent all this stuff. I'm going to close my infinite loop. After I've freed my file name, I'm going to read the next thing if I can. And this is not going to immediately work by itself because there are some extra bytes that are appearing after the file name of the directory entry that we've got. And so I'm going to tell you this, but it's not important for us in general that we have to like move around in this set of directory entries to find the next location here. What's nice about exfat compared to this is that in exfat, all of our structures are exactly the same size. So we read one and do something with it, and then we can just immediately read the next one and do something with it. With ext2, we're going to have to take a little bit of care to start moving around in our file system in kind of a weird way to be able to get to where we want to go. The first thing I'm going to do, I'm going to zoom into my Vim session here. the first thing that I want to do is I'm going to go to this very first lseek call. This took us to the beginning of the block for the root directory's first block. So this is where the start of our directory entry types is. I'm going to declare a new variable right here. I'm going to say offset t, and I'm going to call this record start. lseek returns the offset. There was horrific wailing in the distance, yeah. lseek returns, if you're listening later, it's because there are children in the hallway. lseek returns the resulting offset to where it goes to. So the value that's going to be in record start here is going to be the beginning of the directory entry set for the root directory. This is going to have the value of the block. The first value that it's going to have is this, the root directory's first block value. I'm doing this because what I want to be able to do is after I've read out the file name for this directory entry, I actually want to go back to the beginning of that record. And I want to do this as an absolute offset. I want to do that because the record length field here that's in my directory entry tells me how many bytes from the start of this record do I need to go to find the start of the next record. The string length here is variable, so I can't just go 32 bytes every single time to get to the next record. The record itself can be up to 270 bytes, I think. It can be quite big compared to what we're looking at for the directory entry types here. So I want to go to the beginning of the record that I just finished looking at, and then I'm going to say record start is equal to lseek, again, fd. And this time what I'm going to say is dir entry dot record length and seek cur. So from the current directory entry, from the start of the current directory entry, seek record length bytes, and that takes us the start of the next directory entry. That's going to take us to the start of the next directory entry in this directory. The other thing that I'm going to want to do is I kind of want to keep track of where I am in this file system. I'm just going to run this for now. I'm going to run this. I'm going to write it. I'm going to make it, cross my fingers and hope it compiles. It does. I'm going to run it. I'm going to pipe it into less because we've got an infinite loop here. It's still running in the background, producing gobs and gobs of output. It's not going to stop until it gets to the end of the volume at this point, because it's just in an infinite loop, constantly reading more stuff. But what we're able to see here is we've got these two directory entries, dot and dot dot. These are both pointing back at inode 2. These are self-references back to the root directory itself. The next one here is inode 11, and this is that lost plus found directory that we had. And then finally, we've got readme.md. This is the readme that we actually put into the volume when we finished doing this thing. Notice that the record length here is 4052 bytes. It is way, way bigger than the other ones. And if you add up the record lengths of what we've got here, that actually equals the block size. And if I keep going down here, like I said, it's just constantly going to keep going until the end of time because we have an infinite loop here. So the way that we're going to figure out whether or not we're at the end of a directory is to keep track of how many bytes we have read from this set of directory entries here. So I'm going to make one last variable that's called int32t record lengths. And this is going to be a running sum of how many records I've read and what their total length is. And I'm going to want to stop reading more directory entries once I've read up to record lengths, total sum being the size of a block in this file system. So I'm going to change while1 to be record lengths is less than the block size, 1024 left shifted by superblock.log block size. And what I'm going to do here is just after I print this stuff out, I'm going to say record lengths plus equals dir entry dot record length. I'm going to make this, and I'm going to run it one last time, and I'll pipe it into less again. And if I scroll down here, the end of output is our README file. So that record length of 4052 pushes us past that one block limit that we've got. I'm going to zoom in on here one more time, and I'm going to point out a couple of things that I think are useful in this idea. The main one is, again, for me, separating go to the start of this structure and go to the nth entry in this structure as go to absolute offset and then use seek cur to go to the nth entry here. I find that a lot easier to work with than go directly to the absolute offset and calculate this really long expression. I find that to be easier to work with. You might find it easier to just go to the exact location that you need to go to, but I personally find it easier to work with it this way. The other thing I want to point out is that while we did go through that painful exercise of stepping through this file system in our hex editor and finding these values in our hex editor, that was a helpful exercise because as we were stepping through this and implementing this and building it up, we were able to visually confirm, yeah, 5 is the correct value here. This is what I saw when I was going through this hex dump output. And now I'm able to see it in the code that I'm producing here. And having that value show up is really, really helpful. I find it helpful anyway. All right. Are there any questions about this before we move on to the next part? Yeah. Each of the names is going to refer to a file or directory, and every file or directory has an inode, yes. The direct pointers are coming from when I read the inode for the root directory. So that's this part right here. The inode structure itself has the direct block pointers. When we're going through, and maybe I misunderstood your first question, but when we're going through this loop structure, we're not reading inodes anymore, we're reading directory entries from a block. The directory entries have a reference to an inode number, and to be able to find that information, the direct block pointers for those things, we'd have to go back to the inode table and look up the inode number that we're trying to find. Yeah. Yeah.
I'm a little confused on, in that loop, what exactly are you looping over?
The thing that we're looping over here are the directory entries that are in the block in the root directory. So we've gotten to the start of that location, and we're reading these dir entry types. So I'm going to go back up here. These dir entry types consist of 4, 6, 7, 8 total bytes, and we're reading just that first part, and then we're reading the file name that's just after that. It's the name of the file that's contained within the folder itself, yeah.
And then the actual data you find in inode, which contains the array of blocks.
The direct block pointers, yeah.
Okay.
Yeah.
So we're just getting the names. If we want the data, we go to that instead.
Yeah. So and I'm gonna say this, and please correct me if I'm misinterpreting what you're asking, but we're reading these directory entry types, and once we've read the directory entry types with the file name, at that point, to be able to find more information about the file, we'd have to go back to the inode table and then go to that nth inode. And then once we're at the nth inode, we can read the metadata about the file itself, which includes the direct block pointers. Once we've got the direct block pointers, then we could go back to the block, to the data region to find the actual contents of that file. Yeah. Any other questions? All right, awesome. Okay. So I posted something that looks quite like this on the branch that is attached to this repository, but I will merge that branch into the main branch. So if you look at this repository later, what you're going to see is something that's more like the final product that we've got here. I'm going to pop back to my slides, and our next topic here is to talk about inconsistent file systems. So file systems have a lot of data structures in them that we've been looking at. We've got superblocks and main boot records. This is metadata about our file system. We've got allocation structures. We've got inodes. We've got directory entries in exFAT that mean one thing, and we've got directory entries in ext2 that mean a little bit something a little bit different. And we've got inodes in ext2. Inconsistency of file systems is inconsistency of the data structures in the file system. Inconsistency here is specifically referring to the values in the data structures. Different data structures in these file systems will refer to the same idea. The allocation bitmap, the block bitmap tells us which blocks are used and which blocks are free as a big array of ones and zeros, as a big array of bits. The inodes also tell us which blocks are used and which blocks are free because the inodes have direct block pointers in them. If I go to inode 2, I can see what the direct block pointers are for my root directory. This is another way of finding out which blocks have been used. The superblock in ext2 has a property that says this many blocks are free. The allocation bitmap also is able to tell us how many blocks are free. The inodes collectively can tell us which blocks are allocated. So now we have 3 different data structures that can all report the same information. An inconsistency in our file system is when one or more of those disagree with each other. My block bitmap says there's 30 blocks free. The inodes collectively say there's actually only 28 blocks free. And the superblock says there's 15 blocks free. Now we have an inconsistency of the data structures that are in the same volume. So this is all about the metadata that we have in a file system related to the data structures that are there. I want to emphasize that not writing data to a disk, not actually getting readme.md correctly on the disk, not saving my picture correctly to the disk, that is not an inconsistency. That's important. It's really important to want to get my masterpiece in Microsoft Paint saved to the disk, but not saving it correctly is not an inconsistent file system if all the data structures agree with each other. That's bad. It's really bad, but it's not an inconsistency in a file system. I want to take a really quick look at the 2 file systems that we have been thinking about, and I want to think about what data structures are going to be updated when we do an extend operation on an existing file. So I have a file on my file system, and what I'm trying to do to that file right now is I am trying to append to an existing file. I'm trying to add something to it. So in your mind's eye, I've got that nice picture of Walter, that he's got that little saggy belly hanging out underneath him, and I want to add me to the picture. But I'm going to say that this is big enough of an append operation that it's going to take one additional block or one additional cluster in the file system that I've got. So the file already exists. I'm adding something new to this. So I'm going to pop over here to my tablet, and I'm going to state this a little more directly here. I have a file. The file is called image.bmp, and the 2 things that I'm trying to do this right now are I'm going to open image.bmp and I'm going to open it with this append operation. So I'm adding new data to it. It already exists, and I'm adding new data to it. And then I'm going to write to that same file descriptor. I'm going to add to the end of this file descriptor the new data that I want to add to this thing. In our ext2 or VSFS file system, the approach that we're going to have to do for this is that we're going to have to go through the process of finding this file in the root directory. I'm going to omit that entire discussion because that was what our C program just did. We went to the root directory from the inode table, we went to the block, we listed all the directory contents from that. And then the addition here is we have a conditional statement that says if the file name equals image.bmp. And then that success says, here's the inode for this thing. If I want to append something to the file that I've got, the approach now that I'm going to have to take once I've found this file in my file system is that I'm going to need to update a few different data structures in this file system. The order of operations here is not defined. I'm not saying what's first. I'm not saying what's last. I'm giving you an arbitrary order of operations here in terms of the data structures that are going to be updated. The first thing I need to do is I need to find a free block. I'm adding a new block to this file, so I have to be able to find a free block. The tool that I'm going to use to find a free block is the data bitmap itself. The data bitmap is very quickly going to be able to tell me which blocks are used and which blocks are free. In this diagram, what I've got here is the grayed out allocation. The grayed out bits here indicate that these blocks are currently used. And so the very first thing I'm going to find here is that block number 6 is currently free. And so I'm going to set this bit. I'm going to change that bit in my allocation structure to mark it as used. I haven't written the data yet, but I'm going to mark it as used because I don't want somebody else to come in and also mark it as used or try to find it free, and then we'll collide with each other. The next thing that I need to update, so set this bit as used, I'm going to say that this is operation number 1. The next structure that I'm going to want to update is the inode for this file that I've got. There are 2 properties that I want to update for this file. The first is the set of direct block pointers. I want to be able to say that the second direct block pointer for this file is block pointer number 6. So this is where I'm going to write this data. The other thing that I want to say here is that I'm increasing the size of this file. I'm making the file bigger by however much it is that like stick figure me is going to take to add to this thing. So operation number 2 here is going to be to update the inode itself. The third operation that I'm going to have to do here is the superblock itself has metadata about our file system, including things like how many blocks are free. I need to reduce that by 1. I need to adjust the number of free blocks in my superblock so that when I open this folder up or when I open up my file explorer, it's going to say that there's 1 fewer blocks worth of free space on this file system overall. The very last thing that I want to do here is I want to actually add the data here. And that's where I'm going to actually start writing the data for this extended image. Just before I wrote the data for this extended image, my file system was consistent. I haven't written the data yet. The data has not been written down to the disk, but the file system was consistent. If I opened this file and I crashed before I wrote that, it's going to look really messed up, but my file system is consistent because all the data structures agreed with each other. So that's ext2, that's VSFS in terms of manipulating a file system's data structures. Yeah.
directly go to 6, then there might be actually 5.
Yeah, so like it might be that I put the picture like this. I'm straddling the two blocks here, as opposed to putting it entirely in the new block. There might be free space in the block that's originally allocated to this thing, and I would want to fill that up before I add a new block. The contrived part of this example is that I've already filled the block up with a picture of Walter, and I just want to add a whole new block worth of stuff. If you don't have to add a new block, and that's a fair question, if you don't have to add a new block, the only thing you need to change is this. The only thing you need to change is the file size in the inode itself. Yeah?
What if you're in the edge case where you're like full of direct block numbers and you have to do like a direct?
If you're in an edge case of having to do additional block pointers, so the indirect block pointer structure, you actually have to go through the same general process that we just did, but kind of like recursively. So like you'll have to find a block for the indirect block pointer to go into. Then once you've found that block, mark it as used in the allocation structure, reduce the number of blocks that are free in the super block, update the inode to point to that block pointer, and then have to start finding another block to actually put the data in, update the block that has the indirect block pointers in it, update the super block. So it's the same general idea, but kind of recursively down. Yeah. Yeah.
Will we be doing an assignment with this file system?
With ext2? No. Do you want to? Okay. Because I can make that happen really fast. No, we won't. I mean, I'm going to talk about the next assignment next week. I want to get this one done before we start talking about the next one. But the next assignment, very, very briefly, will be, let's build a shell that uses an exFAT volume as the root of the shell. And I'll give you my code to work with the exFAT, so you'll have something to start with. But no, we're not going to be doing ext2 stuff. So in terms of like assessment of this file system, it's data structures. I want you to be able to tell me a lot about the data structures that we're working with here, if that's ultimately what your question is. Yeah.
In the textbook, the web operation that they have, slightly different orders. Did you mention here first the data bitmap, and then the inode, and the super block?
Yeah.
And then
Yeah.
they do read the inode, data bitmap, and then write the data, but then update the inode.
Yeah, so their approach also includes read operations that I didn't really include here just for brevity. Like you have to read the inode before you can update the inode. When I use the word update in general, I'm trying to say you have to read it, change the value, and then write it back to the disk. And so that the diagram, I'm drawing a picture in my hands here of like it's got columns and there's read and write at different lines here. And there's multiple columns where they're reading and writing from different things. I'm just saying the word update to do all of those operations. But importantly, the order doesn't matter. What's important here is that this is not an atomic operation in any way, shape, or form. Even like reading and then changing and then writing is not atomic by itself. Writing itself, one sector, is an atomic operation, but going through and changing all of these data structures is something that's not atomic at all. So we have to take multiple steps to do that. Okay, so our other file system here is exFAT. And with exFAT doing exactly the same operation, we're going to have to find the file in the root directory. I will leave that to your imaginations right now in terms of that's literally what you're writing to be able to do this stuff. So we'll find the root directories, directory entry contents here. exFAT does have this allocation bitmap. So the question was asked, is this something that's going to show up in the assignment? It's not in the assignment, but exFAT does have an allocation bitmap. It actually has an allocation structure. This is new in exFAT. This is not something that was in FAT32. With exFAT, if we've opened the file, we found it, we're going to have to do a series of updates. Again, arbitrary order here. This is going to be read, update, write. and the order doesn't matter because ultimately none of these are atomic operations. But my approach here is going to be, one, I need to find a free cluster. I want to add a new cluster to this file that exists already. So I'm going to use the 5th cluster here, and I'm going to look in the allocation bitmap itself to find that free cluster. And I'm going to mark that cluster as, I'm going to mark that cluster as used. So I'm going to flip that bit for cluster number 5 to say that this cluster is now used by a file. The next thing that I'm going to have to update is I'm going to have to update the stream extension for this file. The stream extension has the metadata that includes which cluster is the first in the chain, how many characters are in the file name, and what the size of the file is. So I need to update the stream extension here to change the size of the file itself, so the number of bytes that are in this file. I need to change the main boot region, but only maybe, because the main boot region, unlike our super block, doesn't say this is how many clusters are free. Our main boot region just says this is how much % of the volume is used, and it's an integer. Adding one single cluster to our file might not actually change that. It might not change the % in use of this thing. So my third operation here is maybe update the main boot record, maybe. The last thing that we're going to need to do is either change our file so that it has this no fat chain, but I'm just going to pretend that that option doesn't exist for now because I want to update the fat. I want to update the fat. If I'm adding this new cluster here to my file and I've changed the data length, I'm going to need to update the fat itself to add this new cluster to the cluster chain for this file. So that when I get to that offset, now I need to know that I need to go to this next cluster to be able to get the contents of this file. The very last part here is now I need to actually write this data to my cluster heap. And I'll be sad because Walter has just bit me on the arm. He is a bit of a bitey cat. With VSFS, this is a little simpler because a lot of the metadata is in the inode, and it's not scattered in different places like it is with EXFAT. With EXFAT, there's more operations here that we ultimately need to make because this metadata about our file is scattered in different places across our file system. Are there any questions about this? Okay, awesome. I'm going to put this diagram up on the course webpage after today's class. But what I am going to do right now is I've got a few minutes left in class, and that's just enough time to step through some of these, what we're going to see if we did have these inconsistent file systems. So we're going to do this as a Mentimeter. It's the same Mentimeter that we were on just a second ago. I'll pop that back up in a moment. But I'm going to ask you a series of questions, given some constraints or given some descriptions about the file system's data structures that have been updated. And for all of these questions, there are always 4 options. The 4 options are going to be the file looks corrupted. And I'm going to show you the visual picture of what each of these are. The file looks corrupted. So when I open this in Microsoft Paint again, I'm going to see something messed up, maybe part of my original picture, but then a bunch of garbage after that. The file's size is bigger, so the number of bytes that are reported for the file's size has increased. There's less available space on the volume. So when I open my Windows File Explorer open, I'm going to see that there's less space in the drive itself. Or finally, there's no apparent difference. One or more of these options can happen for the different situations that we're taking a look at here. So visually what these look like is corrupted looking file. This is the option, less space on the volume. the picture's file size is bigger, and no apparent difference has no apparent difference. I'm going to hold this up for 2 seconds. I'm going to go back to the Mentimeter, and it should have the code at the top. Okay. What would our human operator see if we were working with VSFS and we had only updated the inode? So we didn't update the allocation structures, we didn't update the superblock, we didn't actually write the data to the file system. I'll give you 10 seconds to answer this question. Okay, 3, 2, 1. That was disappointing. I was expecting it to actually show H, show the responses. Yes, H, that's what I wanted to see. Okay, so yeah, if we updated just the inode, that means that we've updated the size of the file, we've increased the number of bytes. This is part of our inode structure, but we've also updated the direct block pointers here. We updated the direct block pointers, but we didn't write the data to the file system yet. The only thing that we updated was the inode. The less available disk space doesn't happen because the less available disk space is something that we're going to find by looking at the superblock or by looking at the allocation structure itself. For me to go through, or for us to write code that would go through the entire file system worth of inodes to find out which blocks have been used would take way too long. So I just want to use that allocation structure to be able to report how much disk space there is on this thing. Here's a quick question. Is the file system inconsistent? I'm going to give you 5 seconds. 1, 2, 3, 4, 5. This file system is inconsistent, yes. We have data structures that disagree with each other. Our allocation bitmap does not agree with the inodes that we have in this file system. What would happen with exFAT if we had only updated the FAT and nothing else? We didn't update any directory entries in our root directory. We didn't update the allocation structure. We didn't update the main boot record, and we didn't actually write the data to the cluster heap. I'm going to give you 5 seconds. 1, 2, 3, 4, 5. No observable change. Yes, absolutely. There would be no observable change here. exFAT is going to use the allocation structure to tell us how much is free. For it to go through and figure out how many clusters are used from the FAT, even if it could, because we can't because of that no FAT chain bit, if it could, it's going to take way too long compared to just looking it up in this allocation structure that we've got here. The question again, is this inconsistent? 3 seconds. 1, 2, 3. Whoa, okay, we're split pretty evenly here. Is this file system inconsistent? This file system is inconsistent. There's a data structure now, our FAT, which is reporting that there's a cluster in the chain. But the actual rest of our file system, our allocation structure, doesn't say anything about the use or not use of that cluster. I'm going to do one more question here, and then we can finish this up tomorrow's class. In either of exFAT or VSFS/ext2, what would our human operator see if we crashed after just it updating the data bitmap? I'm going to give you 5 seconds. 1, 2, 3, 4, 5. If we update just the data bitmap, we are going to see that there is less available disk space here. Our file system code, our operating system, generally is going to use this allocation structure to determine how much free space there is. With ext2 and VSFS, it might use the super block to calculate that because it's just a simple property that's there. But with exfat, we have to look at this allocation structure. And then one last question here, because it is directly related. Is this file system inconsistent? 1, 2, 3, 4, 5. Yeah, this file system's inconsistent, regardless of the one that we're using. This is a space leak. We have marked a block as used, but nobody can use it now because we've updated our allocation structure, and that block or that cluster is no longer free. We've got a couple more of these questions, but we will take a look at that tomorrow. At this point, though, you should be able to show how common file operations are performed in terms of manipulating a file system's data structures. This is both now from the perspective of reading files. How can I get to a file and find a file in a directory structure? But now also, how do I update an existing file in a file system based on the state of a file system that I've got right now? You should also be able to begin to describe what a human operator might see in files when a file system is in an inconsistent state. In tomorrow's class, we're going to finish up that Mentimeter, and then we're going to start taking a look at process management. In terms of the chapters that are in the textbook for this, there's one chapter that specifically describes the API that's being used for managing processes. It would be helpful if you are familiar with the words fork, wait, and exec. That's all I would expect you to be able to do at this point in terms of those chapters, is be familiar with those words, because we're going to spend time in class doing this live and in person. That's it for today. I hope you all have a great afternoon, and I'll see you tomorrow. Bye, everyone.